Definition and objectives. Surveying, which has also been interchangeably called geomatics, has traditionally been defined as the science, art, and technology of determining the relative positions of points above, on, or beneath the Earth's surface, or of establishing such points. In a more general sense, however, surveying, geomatics, can be regarded as that discipline which encompasses all methods for measuring and collecting information about the physical Earth and our environment, processing that information, and disseminating a variety of resulting products to a wide range of clients. Surveying has been important since the beginning of civilization. Its earliest applications were in measuring and marking boundaries of property ownership. Throughout the years, its importance has steadily increased with the growing demand for a variety of maps and other spatially related types of information, and the expanding need for establishing accurate line and grade to guide construction operations. Surveying plays an extremely important role in many branches of engineering. For example, surveys are required to plan, construct, and maintain highways, railroads, rapid transit systems, buildings, bridges, missile ranges, launching sites, tracking stations, tunnels, canals, irrigation ditches, dams, drainage works, urban land subdivisions, water supply and sewage systems, pipelines, and mine shafts. Surveying methods are commonly employed in laying out industrial assembly lines and jigs. Surveying is important in many related tasks in agronomy, archaeology, astronomy, forestry, geography, geology, geophysics, landscape architecture, meteorology, paleontology, and seismology, but particularly in military and civil engineering. The main objective of surveying is to prepare plans and maps of an area. The science of surveying has been developing since the very initial stage of human civilization, according to the requirements. The art of surveying and preparation of maps has been practiced from the ancient times. As soon as the human developed the sense of land property, they evolved methods for demarcating its boundaries. Hence, the earliest surveys were performed only for the purpose of recording the boundaries of plots of land. Due to advancement in technology, the science of surveying has also attained its due importance. The practical importance of surveying cannot be overestimated. In the absence of accurate maps, it is impossible to lay out the alignments of roads, railways, canals, tunnels, transmission power lines, and microwave or television relaying towers. Detailed maps of the sites of engineering projects are necessary for the precision establishment of sophisticated instruments. Surveying is the first step for the execution of any project. As the success of any engineering project is based upon the accurate and complete survey work, an engineer must, therefore, be thoroughly familiar with the principles and different methods of surveying and mapping. Geodetic and plane surveying. Two general classifications of surveys are geodetic and plane. They differ principally in the assumptions on which the computations are based, although field measurements for geodetic surveys are usually performed to a higher order of accuracy than those for plane surveys. In geodetic surveying, the curved surface of the Earth is considered by performing the computations on an ellipsoid, curved surface approximating the size and shape of the Earth. It is now becoming common to do geodetic computations in a three-dimensional, Earth-centered, Earth-fixed, ECF, Cartesian coordinate system. Geodetic methods are employed to determine relative positions of widely spaced locations and to compute lengths and directions of the long lines between them. In plane surveying, except for leveling, the reference base for fieldwork and computations is assumed to be a flat horizontal surface. The direction of a plumb line, and thus gravity, is considered parallel throughout the survey region, and all observed angles are presumed to be plane angles. For areas of limited size, the surface of our vast ellipsoid is actually nearly flat. 2. Measurement of angles. Determining the locations of points and orientations of lines frequently depends on the observation of angles and directions. In surveying, directions are given by azimuths and bearings. Angles observed in surveying are classified as either horizontal or vertical, depending on the plane in which they are measured. Horizontal angles are the basic observations needed for determining bearings and azimuths. Vertical angles are used in trigonometric leveling and for the reduction of distances to horizontal. Angles are most often directly observed in the field with total station instruments, transits, theodolites, and compasses. The direction of a line is defined by the horizontal angle between the line and an arbitrarily chosen reference line called a meridian. The geodetic meridian is the north-south reference line that passes through a mean position of the Earth's geographic poles. A magnetic meridian is defined by a freely suspended magnetic needle that is only influenced by the Earth's magnetic field. Magnetic declination is the horizontal angle observed from the geodetic meridian to the magnetic meridian. Azimuths are horizontal angles observed clockwise from any reference meridian. In plane surveying, azimuths are generally observed from north. A line's forward direction can be given by its forward azimuth, and its reverse direction by its back azimuth. In plane surveying, forward azimuths are converted to back azimuths, and vice versa, by adding or subtracting 180 degrees. Azimuths can be read directly on the graduated circle of an instrument after the instrument has been oriented properly. Bearings are another system for designating directions of lines. The bearing of a line is defined as the acute horizontal angle between a reference meridian and the line. The angle is observed from either the north or south toward the east or west to give a reading smaller than 90 degrees. The letter N or S preceding the angle and E or W following it shows the proper quadrant. Thus, a properly expressed bearing includes quadrant letters and an angular value. An example is north 80 degrees east. Measurement of distances. Distance measurement is generally regarded as the most fundamental of all surveying observations. In traditional ground surveys, even though many angles may be read, the length of at least one line must be measured to supplement the angles in locating points. In plane surveying, the distance between 2 points means the horizontal distance. If the points are at different elevations, the distance is the horizontal length between vertical lines at the points. 2.1 Methods for making linear measurements. In surveying, linear measurements have been obtained by many different methods. These include 1. Pacing, 2. Odometer readings, 3. Optical rangefinders, 4. Tachometry, stadia, 5. Subtense bars, 6. Taping, 7. Electronic distance measurement, EDM, 8. Satellite systems, and others. Of these, surveyors most commonly use taping, EDM, and satellite systems today. In particular, the satellite-supported Global Navigation Satellite Systems, GNSS, are rapidly replacing all other systems due to many advantages, but most notably because of their range, accuracy, and efficiency. Triangulation is a method for determining positions of points from which horizontal distances can be computed. In this procedure, lengths of lines are computed trigonometrically from measured baselines and angles. Photogrammetry can also be used to obtain horizontal distances. Besides these methods, distances can be estimated, a technique useful in making field note sketches and checking observations for mistakes. With practice, estimating can be done quite accurately. 8. Pacing. Distances obtained by pacing are sufficiently accurate for many purposes in surveying, engineering, geology, agriculture, forestry, and military field sketching. Pacing is also used to detect blunders that may occur in making distance observations by more accurate methods. Pacing consists of counting the number of steps, or paces, in a required distance. The length of an individual's pace must be determined first. This is best done by walking with natural steps back and forth over a level course at least 100 m long and dividing the known distance by the average number of steps. The length of an individual's pace varies when going uphill or downhill and changes with age. For long distances, a pocket instrument called a pedometer can be carried to register the number of paces, or a passimeter attached to the body or leg counts the steps. Some surveyors prefer to count strides, a stride being 2 paces. Pacing is one of the most valuable things learned in surveying, since it has practical applications for everybody and requires no equipment. If the terrain is open and reasonably level, experienced pacers can measure distances of 30 m or longer with an accuracy of 1/50th to 1/100 of the distance. B. Odometer readings. An odometer converts the number of revolutions of a wheel of known circumference to a distance. Lengths measured by an odometer on a vehicle are suitable for some preliminary surveys in route location work. They also serve as rough checks on observations made by other methods. Other types of measuring wheels are available and useful for determining short distances, particularly on curved lines. Odometers give surface distances, which should be corrected to horizontal if the ground slopes severely. With odometers, an accuracy of approximately 1/200 of the distance is reasonable. C. Optical rangefinders. These instruments operate on the same principle as rangefinders on single-lens reflex cameras. Basically, when focused, they solve for the object distance phi in the equation, plus where focal length / and image distance / are known. An operator looks through the lens and adjusts the focus until a distant object viewed is focused in coincidence, whereupon the distance to that object is obtained. These instruments are capable of accuracies of 1 part in 50 at distances up to 50 m, but accuracy diminishes as the length increases. They are suitable for reconnaissance, sketching, or checking more accurate observations for mistakes. D. Tachyometry. Tachometry. Stadia is a surveying method used to quickly determine the horizontal distance to and elevation of a point. Stadia observations are obtained by sighting through a telescope equipped with 2 or more horizontal cross wires at a known spacing. The apparent intercepted length between the top and bottom wires is read on a graduated rod held vertically at the desired point. The distance from telescope to rod is found by proportional relationships in similar triangles. An accuracy of 1/500 of the distance is achieved with reasonable care. E. Subtense bar. This indirect distance measuring procedure involves using a theodolite to read the horizontal angle subtended by 2 targets precisely spaced at a fixed distance apart on a subtense bar. The unknown distance is computed from the known target spacing and the measured horizontal angle. Prior to observing the angle from one end of the line, the bar is centered over the point at the other end of the line and oriented perpendicular to the line and in a horizontal plane. Besides only being suitable for relatively short lines, this method of distance measurement is time-consuming and is seldom used today, having been replaced by electronic distance measurement. 1. Taping. Tapes are now mainly used for the quick measurements of short distances, horizontal or vertical. However, they used to be the most accurate method of measuring all distances, so their use was developed to a fine art by surveyors in the first part of the 20th century. This involves suspending the tape from a tripod at each end under a known tension and reading the point where the tape passed over each tripod using a micrometer. Tape measurements are subject to the following sources of error: inaccuracy in the markings on the tape, variations in the length of the tape due to changes in temperature, variations in the length of the tape due to changes in tension, slope, since it is usually the horizontal component of the length that is required, sag on any unsupported spans, if this is not allowed for in the calculations, errors at the junction of tape lengths. Fabric tapes made of linen or, preferably, fiberglass are used for low accuracy or detail work. Steel bands or tapes are more accurate, but are easily damaged if kinked or trodden on. On smooth ground, an accuracy of about January 2000 is attainable. Taping is performed in 6 steps. 1. Lining in. 2. Applying tension. 3. Plumbing. 4. Marking tape lengths. 5. Reading the tape. And 6. Recording the distance. Using range poles, the line to be measured should be marked at both ends and at intermediate points where necessary to ensure unobstructed sight lines. For accurate results, the tape must be straight and the 2 ends held at the same elevation. A specified tension, generally between 10 and 25 pounds, is applied. Weeds, brush, obstacles, and surface irregularities may make it undesirable to lay a tape on the ground. In those cases, the tape is held above ground in a horizontal position. Placing the plumb bob string over the proper tape graduation and marking each endpoint on the tape. When the tape has been lined in properly, tension has been applied, the endpoint of the tape is marked, and the tape is moved forwarded for another full tape length from the previously marked point. The process of measuring full tape lengths is repeated until a partial tape length is needed at the end of the line. After the partial tape length is obtained at the end of a line, the distance is recorded by counting the number of full tape length and adding the partial tape length. In taping on uneven or sloping ground, it is standard practice to hold the tape horizontally and use a plumb bob at one or perhaps both ends. It is difficult to keep the plumb line steady for heights above the chest. Wind exaggerates this problem and may make accurate work impossible. On steeper slopes, where a 100-foot length cannot be held horizontally without plumbing from above shoulder level, shorter distances are measured and accumulated to total a full tape length. This procedure, called breaking tape, in measuring the distance between 2 points on a steep slope, rather than break tape every few feet, it may be desirable to tape along the slope and compute the horizontal component. This requires measurement also of either the altitude angle or the difference in elevation from which the horizontal distance can be computed. G. Electronic distance measuring. Electronic distance measuring, EDM, instruments measure lengths by indirectly determining the number of full and partial waves of transmitted electromagnetic energy required in traveling between the two ends of a line. In practice, the energy is transmitted from one end of the line to the other and returned to the starting point. Thus, it travels the double path distance. Multiplying the total number of cycles by its wavelength and dividing by 2 yields the unknown distance. 4. Traversing. A traverse is a series of consecutive lines whose ends have been marked in the field and whose lengths and directions have been determined from observations. In traditional surveying by ground methods, traversing, the act of marking the lines, that is, establishing traverse stations and making the necessary observations, is one of the most basic and widely practiced means of determining the relative locations of points. There are 2 kinds of traverses, closed and open. A closed traverse, polygonal or loop traverse, is when the terminal point closes at the starting point. A closed traverse enables a check by plotting or computation, with any gap called the linear misclosure. When within acceptable tolerances, the misclosure can be distributed by adjusting the bearings and distances of the traverse lines using a systematic mathematical method or by graphical method. An open traverse, or free traverse, consists of a series of linked traverse lines which do not return to the starting point to form a polygon. Open survey is utilized in plotting a strip of land, which can then be used to plan a route in road construction. Open traverses should be avoided because they offer no means of checking for observational errors and mistakes. If they must be used, observations should be repeated carefully to guard against mistakes. For point 1, balancing closed traverse. For rough survey, such as a compass traverse, the Bowditch rule may be applied graphically without doing theoretical calculations. According to the graphical method, it is not necessary to calculate latitudes and departures, etc. However, before plotting the traverse directly from the field notes, the angles or bearings may be adjusted to satisfy the geometric conditions of the traverse. In the following figure, A, the polygon ABCDA represents an unbalanced traverse having a closing error equal to AA, since the first point A and the last point are not coinciding. The total closing error AA is distributed linearly to all the sides in proportion to their length by a graphical construction shown in Figure B. In Figure B, AB, BC, C, etc. represent the length of the sides of the traverse either to the same scale as that of the figure A, or to a reduced scale. The ordinate AA is made equal to the closing error AA of figure A. By constructing similar triangles, the corresponding errors BB, CD are found. In figure A, lines EE, DD, CC, BB are drawn parallel to the closing error AA and made equal to E, DD, EC, BB respectively. The polygon ABCD so obtained represents the adjusted traverse. It should be remembered that the ordinates BR, CC, D, E of figure B represent the corresponding errors in magnitude only but not in direction.